Welcome back to The Explainer. Today, we're diving straight into the literal alphabet of the universe. Have you ever just looked around at the incredible diversity of the physical world? You know, the uncountable matter that makes up literally everything, from the water in your glass to the screen you're staring at right now, and wondered, how is it all built? Well, spoiler alert, it all comes down to how individual, completely countable atoms hook up to form molecules and ions.
Here's our roadmap for today. We're going to start by looking at atoms, matter, and mass. Then we'll check out molecules and their allotropes, before moving on to the formation of ions. And finally, we'll decode some chemical formulas. Let's get right into it.
All right, kicking things off with Section 1, Atoms, Matter, and Mass.
Moving right along to Section 2, Molecules and their allotropes. Let's see how these tiny atomic letters actually combine in the real world.
If you really want to understand how elements combine, think of atoms kind of like the 26 countable letters of the English alphabet. They link up to form an uncountable, almost infinite number of words. And in chemistry, well, those words are molecules. Basically, a molecule is just an aggregate of a specific amount of atoms that are held together by chemical bonds. But here's the catch. A molecule absolutely must contain at least two atoms. When they bond, they act together as a single discrete countable unit, locked in by these invisible chemical forces.
Now, check out these models on the screen. Notice the exact geometric arrangement in those ball and stick versions on the left, and then the space-filling models on the right give us a really great sense of their relative size. But whether we're looking at water or methane here, the key takeaway is that we can clearly count the specific number of atoms making up each discrete molecule.
This comparison right here totally hits the nail on the head regarding a really common mix-up. Just look at the difference between having two separate, distinct hydrogen atoms on the left versus a single diatomic molecule of H2 on the right. In that H2 molecule, the atoms are chemically glued together as a single discrete unit. And fun fact, tons of common elements naturally exist as these diatomic molecules, where exactly two atoms are bonded together. We're talking hydrogen, oxygen, nitrogen, chlorine, all the big players.
But nature is incredibly creative, right? Because sometimes a specific amount of atoms of just a single element can arrange themselves into totally different macroscopic shapes. We call these distinct forms of the same element allotropes. Take oxygen, for instance. It can exist as the diatomic molecule O2, which is the stuff we literally breathe to survive, or as a triatomic molecule, O3, which you probably know as ozone.
Oh, and take a look at these uncut diamonds. Diamond is actually an allotrope of pure carbon. It's wild to think about, but it shows how pure, countable carbon atoms, when they arrange themselves in a very specific crystalline structure, create this massive, uncountable mass with insane hardness and totally clear transparency. And get this, another allotrope of that exact same element, carbon, is graphite, the soft black stuff inside your pencil. Same exact atoms, entirely different uncountable matter.
Okay, let's jump into Section 3, the formation of ions. This is where we talk about gaining and losing electrons.
Let's actually walk through how an electron transfer works. Take a neutral atom, like sodium. It starts out with an exactly equal number of countable protons and electrons, meaning its overall uncountable charge is basically zero. But here's the thing about atoms. They absolutely crave stability. To get it, metal atoms like sodium will usually drop a few electrons. In this specific case, it drops exactly one to match the electron layout of the closest noble gas. By ditching that one negatively charged electron, our sodium atom trades its neutrality for an overall positive charge, officially becoming a cation.
On the flip side, look at what goes down with a non-metal element like chlorine. It also desperately wants that noble gas stability. But instead of losing electrons, it's going to gain a specific amount of electrons, again just one in this particular case, to match its own nearest noble gas on the periodic table. Scooping up that extra negative electron tips the scales, giving it an overall negative charge and turning it into an anion.
That brings us to Section 4, monatomic versus polyatomic ions. We're going from simple atoms to much more complex groupings.
So while sodium and chlorine are simple ions made up of just a single atom, we call those monoatomic ions, nature also hands us these much more complex groupings known as polyatomic ions. As you can see from the quote on the slide, unlike those simple monoatomic ions, polyatomic ions are made of multiple atoms bonded together, kind of like a standard molecule, but with an overall net charge. They literally function together chemically as one single discrete entity.
The absolute crucial point here is that when we look at several polyatomic ions, like ammonium or sulfate, we cannot break them apart.
Ammonium, which is 1 nitrogen atom and 4 hydrogen atoms, carries a collective positive charge. Sulfate, which is 1 sulfur and 4 oxygens, has a collective negative charge. So when we're doing chemical calculations or building compounds, these polyatomic ions absolutely must be treated mathematically and chemically as single, discrete, countable units. No exceptions.
All right, final stretch. Section 5, decoding chemical formulas. Time to learn how to actually write these blueprints down.
So we've talked about atoms, molecules, and ions. Now let's decode the actual chemical formulas that chemists use to write them out on paper. In our chemical blueprint, we use the atomic symbols straight from the periodic table, right? And then we follow them up with these small numbers called subscripts. These subscripts indicate the exact number of atoms of that specific element present in the molecule. Oh, and if there's no subscript written after a symbol, that just implies exactly one atom. It's honestly a super efficient way to catalog the ingredients of matter.
But heads up, you gotta be careful here because there are different types of formulas. It is absolutely vital to distinguish between a molecular formula and an empirical formula. The molecular formula lists the true exact number of atoms of each element in a single molecule. The empirical formula, on the other hand, gives you the simplest whole number ratio of atoms in that compound. It's essentially the mathematically reduced version.
Let's look at a really concrete example to clear that up. The molecular formula for hydrogen peroxide is H2O2. That tells us the exact literal reality. One discrete molecule contains exactly 2 hydrogen atoms and 2 oxygen atoms. But if we mathematically reduce that, the empirical formula is just HO. In that empirical formula, the ratio of atoms is perfectly represented as 1:1, right? But it kind of hides the true physical reality of the specific amount of atoms in the actual discrete molecule.
Now, why does this matter? Well, this distinction is incredibly important depending on the type of matter we're dealing with. For covalent molecular compounds, like water or methane, we use molecular formulas because they actually exist as distinct, independent molecules. But for ionic compounds, like sodium chloride, which is just regular table salt, we almost always use empirical formulas. Why? Well, because an ionic compound isn't a single, isolated molecule. It actually exists as a vast, continuous 3D array of cations and anions locked together. There's literally no single molecule of salt. There's only a repeating, uncountable mass where the ratio of atoms is perfectly balanced to maintain a neutral overall charge.
As we wrap up today's explainer, I really want you to start looking at the world a little differently. Consider how these invisible blueprints, a specific amount of a few electrons traded here, the geometric shapes of polyatomic ions there, and these perfectly balanced whole number ratios, how they scale up to build the incredibly diverse physical world all around you. How might it change in just one single countable atom completely alter the uncountable matter you interact with every single day? What other secrets do you think these chemical ratios might hold? Keep exploring, keep asking questions, and we'll catch you in the next explainer.